In this video, we're going to focus on solving some problems with entropy. So feel free to pause the video if you want to try each problem before viewing the solution. So let's go ahead and begin. Which of the following processes is non-spontaneous? So first, you need to know what a spontaneous process is. A process is spontaneous if it can happen on its own without any outside intervention. If it's non-spontaneous, that means it doesn't happen on its own. To make it happen, you have to do work. You got to put in energy to make it happen. So, part A, a ball rolls down a hill. Is that a spontaneous process, or is that a non-spontaneous process? If you put a ball on top of a hill, naturally, on its own, it's going to roll down. So that's a spontaneous process. Now, let's say if the ball is at the bottom of the hill. Naturally, it's not going to go up on its own. It just doesn't happen. So going down a hill is a spontaneous process, but going up a hill is non-spontaneous. Now, it still can go from A to B. It can go up the hill, but you have to put in energy to get it up there. So A is a spontaneous process. It can go down the hill without any outside intervention. It can do it on its own. So we're looking for the process that is non-spontaneous, that won't happen on its own. So we can eliminate answer choice A. Iron metal turns into rust in the presence of air and water. Is that spontaneous or non-spontaneous? So if you place iron metal outside in the air, in the humid environment, will it turn into rust? Now over time it will happen. So that is a spontaneous process. As long as it's exposed to the elements, you don't have to do anything. It's going to turn into rust on its own. Now what about part C? You clean your bedroom. Your bedroom is not going to become clean on its own. In fact, if you just leave a house in there for 10-20 years, it's going to get old, spider webs are going to form, it's just going to over time erode and break down. So your house will not get better over time. Naturally, it's just going to become worse. So it's easy for a system to become disorganized rather than organized on its own. So for your room to become clean, that's a non-spontaneous process because it takes work to clean a room. Your room will not become clean on its own. So C is the answer. Now looking at D, heat flows from hot to cold. That's a true statement, and that will happen on its own. You don't have to do anything to make that happen. So C is a spontaneous process. It's a natural process that will happen on its own. Now granted, you can cause heat to flow from cold to hot, but you got to put in energy to do that. And that's what a refrigerator does. It takes heat from the inside and it uses energy, electricity, to pump heat outside of the refrigerator. So if you look at the back of your refrigerator, you feel that it's kind of warm. And so that's what a refrigerator does. It takes heat energy from a cold environment that is inside the fridge and pumps it to a warmer environment outside of the fridge. But it takes energy to do that. Just as it takes energy to take a ball and pull it up on top of a hill. Now the last one, E. Gasoline reacts with air to produce oxygen and carbon dioxide. Now this happens spontaneously. However, it's a very slow reaction unless you activate it with a spark to speed up the reaction. But hydrocarbons like gasoline, oil, even paper, these things react slowly with air, but because they're so slow, you need to like some type of spark to get the reaction going to speed it up. So this is a spontaneous process, so we can eliminate E. C is the correct answer. Number 2, which system has the highest positional probability? So which system has the highest number of microstates? Now intuitively, if you fill one of these containers with gas particles, the gas is going to distribute itself uniformly. And so a spontaneous process tends to go in a direction that leads to the most probable state. And so the most probable state is answer choice B. Gases like to expand to fill the volume of the container. And the reason why it does so is because that state has the most or highest positional probability, has the greatest number of microstates. And so B is the answer. Now, how can we calculate the number of microstates for each of these situations? So for answer choice A, this particular system, how many microstates does it have? Now, there's only one way in which we can put 4 molecules in one side of the container. Let's say each molecule is given a letter A, B, C, and D. There's only one way in which we can put all molecules in the right side, and the order doesn't matter. So A, B, C, D is equivalent to A, B, D, C. That's simply one microstate. So we're dealing with combinations as opposed to permutations. So A has one microstate. Now what about system C? How many microstates does it have? Now we only have one molecule on the right side, 3 on the left. So we can put molecule A on the right side, and on the left, that means B, C, and D has to be on the left. If we put B on the right side, on the left it has to be A, C, and D. If we put molecule C on the right side, on the left has to be A, B, D. And if we put D on the right side, on the left has to be A, B, C. So as you can see, there's 4 microstates. There's 4 ways to make this happen. We can have A on the right, B on the right, C on the right, or D on the right. Now C and D, they're equivalent because you just got to reverse the direction. They both have 4 microstates. Now let's focus on system B. Let's see how many microstates it has. So let's say this is the left side and this is the right side. So on the left, I can put AB, or I can put AC, or AD. If I have AB on the left side, that means CD is on the right side. If I have AC, then BD is on the right side. And if AD is on the left, that means BC is on the right. On the left side, I can't have BA. BA and AB are the same. I could put BC or BD, and then I could put CD on the left. So if I have BC on the left, AD is on the right. If BD is on the left, AC is on the right. And if CD is on the left, that means BA is on the right, or AB is on the right. So as you can see, there's a total of 6 microstates to achieve this system. So that system has the greatest number of microstates. So it has the highest positional entropy. And that's why that state is most likely to exist out of all states. So here's a question for you. Let's say if we fill the left side with 4 molecules. Is it possible for this to occur? Can all 4 molecules end up on the right side? Is that possible? And would you say that process is spontaneous? Now, it is possible for that to happen. All 4 molecules can end up on the right side. However, it's not probable. It's possible, but it's improbable. It's unlikely for it to happen, because this state has the highest number of microstates. So this system is going to go towards this state. Now, if we look at which of these 2 states is more favorable, they're equal. This has 1 microstate, and this has 1 microstate. So these are equally likely to occur. However, the system is going to go towards the state that is most probable to occur. So whatever event is most likely to occur, that's what's probably going to happen. So because this system has 6 microstates, it's spontaneously going to go to that system because it has a higher probability of turning into that system. So spontaneous processes tend to flow in a direction from low entropy, entropy is represented by the symbol S, to high entropy. So as you increase the number of microstates, the entropy of the system increases. So it turns out that the driving force for a spontaneous process is an increase in probability. So probability is the driving force. And disordered states are more probable than ordered states. For example, there's so many ways in which you can disorganize your room, but there's less ways to organize it. And that's why natural processes, natural spontaneous processes, tends to flow in the direction towards higher entropy or more disorder. A good example to illustrate this is if we flip 4 coins. So for example, let's say if you take 4 pennies and you toss it into the air. Now, how will these 4 pennies land? Is it possible that they can be well arranged, all 4 heads or all 4 tails? Or do you think it's more possible that they're going to be disorganized into a mixture of heads and tails? So which event is more probable? Having 4 heads, 4 tails, or 2 heads, 2 tails, or 1 tail, 3 heads, or let's say 1 head, 3 tails? So which state has a higher probability, or which one has more entropy? Is it the more organized state where they're all the same, or a more disorganized state where they're all different? Now let's calculate the probability of getting 2 heads and 2 tails compared to a more organized system of getting 4 heads. So what we need to do is list out the possibilities. So we can have all 4 heads. This is possible, just not probable. Or we can have 3 heads and tails. We can have heads, heads, tail, heads. Or it could be 2 tails. It could also be like this. So these are half of the possibilities. We could also have tails in front. As you can see, there are 16 possibilities because we have 4 coins and each coin has 2 states, either heads or tails. So it's going to be 4 squared, which is actually not 4 squared, but 2 raised to the 4th power. And that's why we have 16 possibilities, because there's 2 states, heads or tails, for each of the 4 coins. Now, notice that there's only one microstate that corresponds to this highly organized state of all 4 heads. Now, the most disorganized state is when we have 2 heads and 2 tails. So I'm going to highlight this in green. This occurs here. And we also have it here. And we also have it here as well. Notice that this is equal to the same number of microstates in the problem where we had 2 molecules on the left and 2 molecules on the right, because we were dealing with 4 molecules. In this case, we're dealing with 4 coins. And so a disorganized state has a higher number of microstates than a more organized state. This is similar to putting all molecules on one side of the container. And so entropy is basically associated with probability. So the reason why natural spontaneous processes tend to go in the direction of higher entropy is because nature tends to seek out the state that is most probable or more likely to occur. If you toss 4 coins in the air, it's most likely that you're going to get 2 heads and 2 tails. And chances are that's probably what's going to happen. So that's why natural spontaneous processes tend to flow in the direction of higher entropy. It's simply because a disorganized state has a higher probability of occurring than an organized state. Now, the second thing that you have to realize is that the probability of a disorganized state occurring increases with the number of molecules or the number of coins. So for example, if you have one coin, then there's a 50% chance it could be heads or tails. Now let's say you have two coins. To get two heads, the probability is 1/2 raised to the second power. And to get heads or tails, the probability is simply 1/2. So you have a 1/4 chance to get an organized state being two heads. And there's a 1/2 chance of getting a disorganized state where it's a mixture heads and tails. So here it's 50% to get a disorganized state and only 25% to get an organized state. Now if you wish to know how to calculate probability, you need to make a list of the possible states. It's either heads, 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 tails, tails, heads, tails, tails. So there's 4 possible states, and there's only one microstate that leads to 2 heads. So it's 1 out of 4. And to get heads, tails, or tails, heads, there's 2 possibilities out of 4. So 2 out of 4 gives us a probability of 1/2 or 50%. Now notice what happens if we increase the number of coins. Let's say if we use 3 coins. Now, to get an organized state like 3 heads, there's only one microstate that leads to that. And there's a total of 8 possibilities because we have 3 coins and each coin has 2 states, heads or tails. So it's 2 to the 3rd, which is 8. So it's 1 out of 8. 1 out of 8 is 0.125. So if you multiply that by 100, that leads to a probability of 12.5%. Now let's say if we have 4 coins. To get an organized state, it's going to be 1 out of 2 to the 4th power, which is 1 out of 16. And so the probability of getting that is 6.25%. Now let's say if you have a mole of coins, 6 times 10 to the 23 coins. So the probability that all of them will be heads is going to be 1/2 raised to the number of coins, which is 6 times 10 to the 23. So basically, that's going to be about 0 because we have such a large number on the bottom. So as the number of coins increases, the probability of getting an organized state decreases. It's 25% for 2 coins, it's 12.5% for 3 coins, it's 6.25% for 4 coins, and it's approximately 0 for a mole of coins. So when you're dealing with a bunch of gas molecules, let's say a mole of gas molecules, it is highly improbable that all the molecules will be on one side of the container, just as it's highly improbable for a mole of pennies to all be heads. However, if you have a small number of coins, it's possible that you can get all heads. It's not probable, but it's still possible. So if you have like 4 molecules, it's possible that all 4 can end up on one side of the container. It's just not probable. Number 3. Which of the following statements is true? Well, before we answer this question, let's go over the second law of thermodynamics. So let's say we have 2 substances where A converts into substance B. So this would be a spontaneous process since it's going in the forward direction and it's happening without any outside intervention. Now sometimes you could have a reversible reaction where A converts to B and B is converted to A. So in this case, we could say that the system is at equilibrium. And for the third case, the reaction could be going to the left, which means that it's non-spontaneous in the forward direction, but it is spontaneous in the reverse direction. Now, for the first situation, you need to know that the change in the entropy of the universe is positive for a spontaneous process. And that's the basic idea behind the second law of thermodynamics as it relates to entropy. For the second case, the change in the entropy of the universe is 0 for a process at equilibrium. Now, for a process that is non-spontaneous, the change in the entropy of the universe is going to be negative. So knowing that, we can analyze certain statements. Like the first one, answer choice A, the change in the entropy of the universe is equal to 0 for a spontaneous process. Well, we know that for a spontaneous process, the change in the entropy of the universe is going to be greater than 0. It's positive, which means answer choice A, that's a false statement. Now for B and C, let's see, the change in the entropy of the system is always positive. Well, that's not true. It could be positive or negative. And for C as well, the change in the entropy of the surroundings is always negative. It can be both positive or negative. And with that in mind, let's go ahead and take some more notes. The entropy of the universe is the sum of the entropy of the system plus the entropy of the surroundings. So that equals the change in the entropy of the universe. And let's discuss the spontaneity for the different scenarios that we're going to talk about here. And let's turn this into a table. Now, if both the change in the entropy of the system and the surroundings is positive, the change in the entropy of the universe is going to be positive, and therefore the process will be spontaneous. Now, both of these could be negative, the change in the entropy of the system and the surroundings, in which case the change in the entropy of the universe will be negative. In that case, the process will not be spontaneous. Now, the change in the entropy of the system can be positive, and the change in the entropy of the surroundings could be negative, or vice versa. When the signs are different, whether the process is spontaneous or not is conditional. It really depends on which one has a greater magnitude. So for instance, if the entropy of the system, the change in the entropy of the system rather, if it's greater in magnitude than the change in the entropy of the surroundings, then the change in the entropy of the universe will be positive because this is a greater value. Thus, it will be spontaneous under those conditions. Now, for the last scenario, in order for this to be positive, the change in the entropy of the surroundings, the magnitude of that has to be greater than the magnitude of the change of the entropy of the system. Then the whole process will be spontaneous. But what you need to understand is that the change in the entropy of the system and the surroundings can be positive or negative. They're neither always positive or always negative. They can be both. So B and C are false statements. Now, D is the true statement. The change in the entropy of the universe is negative for a non-spontaneous process. We talked about that in the previous slide before I created this page. So for a non-spontaneous process, it's going to be negative. But for a spontaneous process, the change in the entropy of the universe is positive. And we can see that here. If delta S of the universe is negative, it's not going to be spontaneous. So D is the answer. It's the true statement here. Number 4. Identify each statement as true or false for a system undergoing an exothermic spontaneous process. So with this information, the fact that we know the process is spontaneous and exothermic, how can we determine whether the entropy of the system, surroundings, the universe, if they're going to increase or decrease? Well, first let's talk about the system. In order to determine the if the entropy of the system increases or decreases, you need to identify the direction of heat flow. Whenever heat flows into the system, the change in the entropy of the system is going to be positive, which means the entropy of the system increases. Whenever heat flows out of the system, the entropy of the system decreases. And the same is true for the surroundings. If heat flows into the surroundings, the entropy of the surroundings goes up. If heat flows out of the surroundings, the entropy of the surroundings goes down. So now let's talk about the situation that we have here. So I'm going to draw a box. Everything inside of this box is going to represent the system. Everything outside of the box will represent the surroundings. Now, the process that we're dealing with is an exothermic process. Because it's exothermic, we know that heat energy is going to be released from the system. Let's say the temperature of the surroundings, let's say it's room temperature, it's 25 degrees Celsius. If we have an exothermic process, would you say the temperature of the system is greater than or less than 25? In order for the system to release thermal energy, its temperature has to be greater than the temperature of the surroundings. And let's pick a value. Let's say it's 100 degrees Celsius. That means the system is relatively hot compared to the surroundings, and we can say the surroundings is relatively cold. Heat is always going to flow from hot to cold. So heat is leaving the system, going to the surroundings. Because the system is releasing heat energy, we could say that it's exothermic. Now, since heat is flowing to the surroundings, we know that the entropy of the surroundings will increase. Therefore, the change in the entropy of the surroundings will be positive. Heat is being removed from the system. So because the system is losing thermal energy, the change in the entropy of the system will be negative. So that means the entropy of the system is decreasing. As heat flows to the surroundings, the temperature of the surroundings is going to go up. As the system loses thermal energy, the temperature of the system is going to go down. So notice that temperature and the change in entropy, there's a relationship here. When the temperature goes up, the entropy goes up, which means the change in entropy is going to be positive. Thus, substances at higher temperatures will therefore have a higher entropy value. But now let's go ahead and identify each statement as true or false. So for answer choice A, or statement A rather, the entropy of the system increases. That's not true. The change is negative, so it decreases. A is false, which means that D is a true statement. Now looking at the surroundings, the entropy of the surroundings increases. B is a true statement. We see delta S of the surroundings is positive because heat is flowing to the surroundings. Now for E, the entropy of the surroundings decreases. That can't be true. If B is true, E has to be false. Now what about C? The entropy of the universe increases. We don't know the relative magnitudes of these two. So looking at the signs of delta S of the system and delta S of the surroundings, we can't tell which one is bigger. However, we were told that this process is spontaneous. And based on the second law of thermodynamics, as it relates to entropy, the entropy of the universe always increases for a spontaneous process. So C is a true statement as well. Therefore, B, C, and D are true statements in this problem.